Bem, boa noite a todos, bem-vindos a mais um seminário do ciclo promovido pelo Departamento de Economia sobre a COVID-19. Para nós é um prazer termos tantas pessoas interessadas nesse assunto, que eu acho que tem vários desdobramentos econômicos e vários desafios das mais variadas formas. O seminário de hoje vai ser um seminário sobre os métodos, sobre a econometria da pandemia. E a gente tem o prazer de termos o Marcelo Medeiros, da PUC, e o Thomas Mellan, do Imperial College. O seminário vai ser em inglês, so I'm going to turn to English. It's a real pleasure to have Marcelo and Thomas. Thomas, thank you so much for taking the time of joining us on this webinar. As usual, we'll have first the presentations by Marcelo and Thomas of about 15 to 20 minutes each one, and then we'll follow with Q&A. During the Q&A session, we'll have people raising hands, and then I'm going to open up the mic so they can ask the question themselves, right? So just to remind that we put in our system, probably you are all aware of it, we put in the system, the webpage of the department, we put the links for the videos of the previous seminars are already there, as the new seminars that will follow in the upcoming weeks. So next week we're going to have Claudio Ferraz and Felipe Campanche talking about the political economy of the COVID-19. So I think we already reached a stable number of participants. So why don't we start, Marcelo? Thanks a lot for having this.
Okay, thank you. Good evening to everyone, and it's a pleasure to be here. I would also like to thank Thomas Mellan to kindly accepted to give this webinar together with me. So what I'm going to talk about during this 20 minutes, a little bit about the initiative that some colleagues and I had at PUC-Rio to try to understand the evolution of COVID-19 in Brazil, and we proposed a very simple statistical model to forecast the evolution of the disease in the very short run, meaning the next 14 days. And this first attempt to understand the evolution of the disease is a joint project with colleagues that are here. So from the Department of Electrical Engineering, Department of Industrial Engineering, the University of California at Riverside, and also from the Department of Economics as well. So this is the original group who started to analyze this data. And we have also now some new members that join forces because we have more and more data. I'm going to talk a little bit about that. So we have people from other universities as well. And so what's the idea? What was the driving force for us to try to come up with a model? Okay, of course, forecasting the evolution of the cases and deaths in the short run, in the few days ahead, is crucial to manage the health system. For instance, to have a field hospital put together, we need at least 14 days. So it's important to know how many of critical cases we're going to have, like people needing intensive care. So that was like the challenge. So with this in mind, we are not epidemiologists, okay, so we're mainly statisticians, econometricians, economists, and data scientists. So we try to use just the data, okay, and come up with a statistical model looking at the behavior of the data and see what the data can tell us about the evolution, and comparing the data in Brazil, the evolution of the disease in Brazil, with other countries that are ahead of Brazil in terms of the disease evolution. So we define this the kind of a latecomer country a country where the disease started after. So we start to see cases of COVID-19 in Brazil after some other countries. So we are going to use this information into this model that I'm going to describe to you tonight. Okay? So there are some advantages of doing that. First of all, you have something that's kind of structure-free. So in the to economists, like a reduced form model. So we are not going to set or tune any structural parameter. So it's just based on the data. So we are going to avoid this parameter tuning. So everything based on statistical estimation. And because of the nature of the data, you all know that Brazil is under testing a lot. So basically only people that go to the hospital get tested, and not all of them, probably only the ones that are kind of in the more advanced stage of the disease. So basically these individuals are the ones who are pressing the health system. And that's the data that we basically have. So if you think about the total number of cases in the country, there's a lot of measurement error, but we are going to try to use this in our favor. Say, okay, we are looking at the data, the cases about these patients that are really pressing the health system. And another advantage is kind of be quite simple. It's just equation, and so it's simple and cheap to be implemented. On the other hand, of course, there are advantages. Nothing's perfect. The model is sensitive to structural breaks. It will take the model is adaptive, but it will take quite some days to get the model to full adapt to a new reality, to a new situation. And of course, if we are kind of in a very short span of time, so any outlying observations, any observations that are not in the normal, this will have an impact in the whole estimation, but we try to mitigate this a little bit. And of course, there's no information about lockdown timing and other public policies. This can be incorporated in the model in a second stage of our modeling strategy. We are going to try to include some of these techniques. Okay. So let me tell you what's the key idea. So that plot that you're seeing on your screens is just the evolution of the number of cases for some countries, and Brazil as well. Okay, and it's basically in calendar time. So it's kind of like the daily. Here you have the days and the number of cases. Okay, but if you look at the circle dots here, these are the days where we observe case number 100, when we have like 100 people infected. Okay, so what we are going to do is we are going to measure the evolution of the curve in terms of days after that date. So we are going basically to shift the curves to make all these circles on top of each other. Okay, so that's what we have when we do that. So then you see that you have the curve for Brazil here and the curve for the other countries there. Okay, so in a sense, they are kind of in the future. So if we look at this case time, not calendar time, in this case scale, some countries are ahead of time with respect to Brazil. So that's the idea, that we are going to use this information. So basically, we are going to see how Brazil relates to these other countries. Okay, it's not a perfect relation, but you're going to see how many, in which proportion each of these countries can explain a little bit of the evolution of Brazil. And then we are going to use this to project what's going to happen to Brazil for the future, where this is this shaded blue area here. And that's what we have. That the dashed line is represents the forecast. Okay, so that's the overall idea, okay? And we have 31 countries ahead of Brazil, 17 are 7 days ahead, 7 are 14 days ahead, okay? And when we use these countries, we discard China and France. China has a lot of data problems. In France, there's some measurement problems in the cases because you have like total cases going down in some days, which kind of makes no sense. So we remove these 2 countries. And also in terms of generality of the method, we have, like, as compared to Brazil, we have 152 other countries that are behind Brazil. So in a way, they can also use this methodology if someone thinks this is useful somehow, okay? So I promise that to be the only equation that I'm going to show you, but that just to give an idea, what's the model? Very simple model. It's a log linear model. So basically the daily growth rate in the number of confirmed cases, okay, it will be a function of the daily growth rate in the confirmed cases of the peers of the other countries. Remember, this is all in case time, it's not in calendar time, okay? And you have a kind of a discrepancy measure of what happened in the previous day. So basically, that's the model. We estimate this model in a rolling window. There are some technicalities. I'm going to basically skip the technicalities here, but I'll be extremely happy to discuss all of these with anyone interested. Data, we use only data that are widely available, so the Ministry of Health in Brazil and Johns Hopkins University in the US, okay? And these are kind of the forecast made yesterday for the next 14 days. So we are forecasting the next 14 days. That's the forecast for the confirmed number of cases. So we are going to reach, if you take here the limit of the confidence interval, we are passing the 200,000 number of cases. That's what the model is pointing to, okay? And here there's kind of a tricky graph. That's the confirmed new cases. So we see that for the next week, the cases will start to grow, and there's some evidence that start to go down after the first week. This should be taken with a lot of care because what happens here is that all the peers, all the curves of all these peers that are ahead of, in time as compared to Brazil are all starting to get to go down. So of course we are going to see this movement here. Probably in the next few days this may change, but that's the picture as of today. That's what we see that the model is telling us in terms of new cases. And these are numbers. If you are interested, these slides will be available. Anyone interested? So we are going to have like around 6,000 new cases in 14 days. This is the same picture for deaths. The shape is more or less the same. Okay, and then we are forecasting in 2 weeks like 14,000 deaths. Okay, so but you may say, okay, but what Brazil is heterogeneous. There's a lot of heterogeneity in Brazil, and we acknowledge that. And some different states in Brazil are also in different time points in this case time scale. So if you compare, and this heterogeneity can be seen quite clear if you compare the forecast for São Paulo and the ones for Rio. São Paulo started to notice the cases of COVID-19 before Rio, and you see that for São Paulo, we are really seeing that decrease in the curve that's caused because of this relation with the countries that are ahead of us. But Rio, as Rio is behind, it's also behind in terms of this case scale. So for Rio, you still see upward trend here. Okay, we have data for all the municipalities of Brazil, and we are looking at the model for different municipalities, different groups of municipalities. Okay, just for you to, but how good is this model? Okay, you have these forecasts, but they're not crazy. These forecasts are meaningful. So we have a back test, and we have full disclosure of all these. If you go to the website covid19analytics.com.br, we have all the forecasts from day one of this project. These forecasts have not been revised, so you have all the spreadsheets from the first day there, where you can see all the forecasts that we made at that specific date. And what I'm showing you is the back test for that. So on average, in terms of cases, we have an error that's 7.62% for the whole month that we have been doing this for a month. So we have like 7.6%. If you take just the last 14 days, we have 8.5. And in terms of deaths, we have like for the whole sample 12%. But we have been very lucky in terms of forecasting the last 2 weeks, and this percentage error dropped to almost 6%. Okay, so we believe for that level of uncertainty that we have in this data, in this model, I think we are the results are somehow pretty good. Okay. To wrap up and give some directions what we are going from here. So conclusions, our forecasts are very short-term time series extrapolations, no structure, no epidemiology background at all. These models are constantly being updated. All the updates can be seen in the website, and the paper is on archive. A new version will be uploaded soon. There are some other papers available with this more statistical take on the problem. One is from the Fed Richmond, and the other one is from Jürgen Dornick and co-authors from Oxford University. Okay, so the last thing I would like to say is that Brazil is a country with continental dimensions, highly heterogeneous. And it's important to take into account this heterogeneity, how we can do that. So we have like different levels of different curves. Probably there are many curves in Brazil. At least we can think about like two clear curves. How we take into account this heterogeneity? We can, of course, try to impose some structure in the model and more priors in a way, or include some nonlinearities, or we can try to figure out if we have some data that we can look for this heterogeneity. And we have data now from the municipal level. So this is an example. This is the distribution of cases over the municipalities in Brazil. So you see here that there's a lot of blue colored cities. So cities with no cases. So if you believe that this is going to spread, so probably that kind of top on the curve that I showed you, the peak is not, it won't be the peak. That's the peak of one of the many curves that we have. But if we look into this heterogeneity, maybe there are some other parts of the countries where you're going to see the peak much further into time in the future. Okay, so these are the cases per million. So you just divide by the population divided by million, and that's what you see the distribution. And we have the same thing with deaths. So we have the history of these cases. So this is a kind of a screenshot from the beginning of the week. So we have the time series evolution for all municipalities. And what we are doing now is exactly to look into the curves and see how we can estimate all this heterogeneity that we observe in the data. So basically, I hope I didn't cross my limit. So I would like to thank you very much. Thomas, the floor is yours.
Thank you, Marcelo. Thomas, please.
Excellent. Thanks very much for that presentation, Marcelo. Okay.
Marcelo, you need to stop sharing.
Yep. Thank you. Yeah, so as I said, thanks very much for that presentation. And it's a real pleasure to be here to speak to everybody tonight. So I'm going to talk a little bit about some of the modeling that we're doing at Imperial College. So I'm part of a group of computer scientists and epidemiologists and statisticians. That is these guys listed here. And we're a small part of the general COVID response team at Imperial. So there's streams working on all different kinds of things, from looking at mobility data to trying to look at virus epidemiology, to all different things. But the approach that we're taking is a kind of statistical one. Based on the renewal equation. So that's what I'm going to talk about. So there's a couple of people here that are Brazilian, so Henrique and Nuno. So they've been extremely useful in trying to inform what we're doing in Brazil. So far we've concentrated on Europe, but at the minute, going forwards, we're trying to look at different places. Okay, so I can just tell you a little bit about the philosophy of our modeling approach to start off with. So the general philosophy is that we're trying to do something that's principled, in the sense that the equations that we use to describe this, the spread of this disease can be derived from first principles. So from the simplest processes you could imagine that could reasonably describe the spread of a virus. So you start off with one seed infection, and that infection, after some random amount of time, infects some random amount of other individuals. And this spreads and goes on. And this kind of age-dependent branching process, which was worked out like in the 1950s by people like Mellan and Harris to describe nuclear fission. This is exactly what we need to describe a viral spread on the most basic level. And if we look at the expected number of cases that we get from this kind of microscopic picture of the interactions, we can derive what's called the renewal equation for infections. So this renewal equation is particularly simple in form. In fact, it's deceptively simple. It says that the number of cases at some time t, so the number of cases, for example, now, is equal to the number of cases at previous times convoluted with some generating process for the infections. So what does this mean? It means that the number of cases now is equal to the sum over all of the previous cases times some process that describes how infectious they are. And really everything that we do in the group that I'm working on to describe COVID is based around this really simple equation. So as well as it being hopefully principled in theory and simple, we also take a probabilistic approach in so much that, of course, in our model there are parameters, and these parameters are unknown. And we simulate from these using Markov chain Monte Carlo, and it allows us to make predictions that have some posterior density and give us confidence intervals. So that's the general kind of method that we're trying to use. Specifically for the model that we've made our most recent predictions on, which was predicting the reproduction number and the number of cases in Europe. This is the basic structure of the model. So we have modeled infections, which obey a renewal equation like I just described. And we have some generating process, which is broken down into the reproduction number and the serial interval distribution. So the serial interval distribution says, if I'm infected now, how infectious am I to other people tomorrow? And am I more infectious the next day? And then am I most infectious perhaps after 5 days, something like that with COVID. So it's the temporal distribution of infectiousness is in the serial interval distribution. And as well as that, the infectiousness profile has what I like to think of as a kind of magnitude. And this magnitude is the basic reproduction number. So if I'm infected, how many people will I infect on average? And for coronavirus, this is about 3 in most countries before any interventions or change in behavior. And generally, it drops to about 1 or a little bit above or a little bit below, depending on how the population of the country behaves. So this is built into our model, and our reproduction number is parameterized to try to take in as much information as possible. So we take into account covariates like whether or not a government has imposed lockdown, or whether or not they've said universities should close. So we try to take in all of this information in parameterizing our reproduction time. So, and another key part of our model is that we model deaths. So one of the big difficulties with coronavirus has been that the reported cases are often quite far from what the true number of cases is. Of course, it's important to be able to understand what the reported cases are and will be in the future, but it's probably a very small fraction of the true number of cases. And we believe that the number of reported deaths attributed to coronavirus is probably a more accurate measure. So if we can create or understand the relationship between the deaths and the infections, which is going to be some kind of convolution, then we have a chance of trying to model the underlying processes. Okay, so that's the kind of overview of the model. I can just give you I'm not going to do too much maths in this. We're going to talk about some results in a second, but I can, for the mathematicians in the audience, I can just give you a quick rundown of the basic equations. So the number of cases at some time, t, for some country, is equal to a convolution, so a sum of the number of cases at previous times times a serial interval distribution. So this is how infectious you are as a function of time, times the reproduction number, and times this discount factor, the number of susceptible individuals. So our reproduction number takes this form. We have a basic reproduction number, which is going to be the number at the start of the epidemic, which, as I said, is around 3. And then we just parameterize the form of this. I mean, ideally keeping it as simple as possible. I mean, we could make this really complicated and put in a Gaussian process here, or we could do anything. We just want to keep it as simple as possible. So we have these interventions, which are these things down here, and we have a linear model. This is how we parameterize our RT. Whether or not we make this super complicated or we keep it fairly simple, we get pretty similar results. So generally, keeping it as simple as possible is the way to go. As I said, the number of susceptible individuals. So as the number of cases increases, the reservoir from which new people can become infected decreases. So we take into account this factor. And for the serial interval distribution, which is the infectiousness profile, this is a gamma distribution with mean 6.5 days. Of course, we could fit these parameters and derive them from the data, and that's another thing that we do. But these particular parameters are taken from epidemiological studies that other people in the group at Imperial College have done. Okay, so as I said, we know the cases, but we don't want to fit to cases directly when we're working out RT, because different countries have different levels of case underreporting. It's very difficult to estimate. So what we do is we try to fit to deaths, and we relate deaths to the cases by a convolution of the cases with a death distribution. So if you're infected, how long will it take you to die? And times the infection fatality ratio. So the distribution for if you're infected, how long does it take you to die, is the infection to onset distribution plus the onset to death distribution. And again, we take these from epidemiological studies that our colleagues at Imperial College have done. Okay. So that's basically all of the technical stuff and all of the maths out of the way. So I can just emphasize a little bit. So in this model, we use reported deaths, and the other source of data would be, for example, intervention covariance. So they're listed here for a number of different countries in Europe, and you can see every country implements different interventions at different times. So Germany was on the ball pretty quick. UK, by contrast, implemented any interventions such as lockdown a lot later, and that naturally has effects on how the disease progresses. The way that these interventions are included in the model, so each country So they're included in a partial pooling scheme, or the effect, each country has its own effect, but also there's shared effects. So this is a little bit like what Marcel was saying about sharing the effects between different countries. Okay, so I mean, we can start to look at some of the results that we've produced with this model. This is Italy, and I believe that this is produced up until current time, or at least yesterday. And you can see the number of deaths in Italy. So I mean, let's start here on the right. The number of deaths in Italy peaked at almost 1,000, and we can fit the number of deaths fairly well. And from this the deaths that we're predicting here, we can estimate the number of daily cases. And you can see the number of daily cases is large. If we look at the number of reported cases, you can't really see it because it's so small. So if we consider the number, the progression of the disease in terms of the daily deaths, we can see around the 30th of March, something's happened and the number of deaths has started going down. And we can relate that to the number of cases. So in general, there's a lag of about maybe 3 weeks between anything that happens with the number of cases and happens with the number of deaths. So if we look at the number, I mean, when do the deaths start going down? The deaths start going down about 3 weeks before the number of cases. And in our model, we see that this change in the number of infections, the change in the number of infections happens whenever there's a change in the reproduction number, and the reproduction number occurs whenever there's some interventions introduced by the government. For example, we can see the effect of, so we can try to identify the effect of different interventions. School closure, for example, is here, and encourage self-isolation. We see that the biggest effect in general is complete lockdown. So complete lockdown is at the end. That's generally the last intervention the country takes. And in Italy, it was only after lockdown was implemented. So after people were told, you really have to stay at home and you can't go out and you shouldn't be going to work. After this was implemented, the reproduction number went below 1. And when the reproduction number goes below 1, the number of cases drops, the disease becomes under control, and 2 to 3 weeks later, the number of deaths starts dropping. We can compare this to somewhere like Sweden. So in Sweden, the number of deaths is still increasing. I mean, Sweden has some problems because in their data, there's a huge amount of noise, and there might be problems with the reporting of deaths in Sweden. But we can see that in essence, the number of deaths is still rising. The number of cases that we're predicting is still rising, and the reproduction number is still above 1. So we expect this epidemic to keep growing in Sweden. And the difference really between somewhere like Sweden and Italy is if you look at the interventions that have been taken in Sweden, there's been no complete lockdown. So they've encouraged social distancing, so work from home if you can, but there's no complete lockdown in the same way that there has been in other European countries that have really started to bring down the number of cases and deaths. Okay, so I mean that's the situation in. Lastly, to say that I mean I think I've made this point already, but really the biggest, the most identifiable effect that we can see from the data is lockdown. Everything else, it doesn't really matter. They're kind of exchangeable, and you can't really tell the difference between one and another. But the effect of lockdown is substantial. Okay. So I mean, we can consider how the model that we have might be different if we try to apply this to Brazil. So in Brazil, there's a number of differences. So we expect, for example, the infection fatality ratio to be different. So if you're infected, what's the chance of dying? This is, of course, different in every country. If we compare, for example, the UK population pyramid to the Brazil population pyramid, The Brazilian one is much younger, and younger people don't die as much. So this is going to affect the infection fatality ratio. There are also other things that affect the infection fatality ratio that are different. For example, the contact matrices. So what is the contact between all of the different age groups? So what's the contact between the 15 to 20-year-old age group with 50 to 60-year-old age group? This is different for different countries, and it's very difficult to get hold of this data. So we have it for the UK, and we have it for a number of countries, but we don't have this for Brazil, although we have it for some South American countries, so we can try to estimate. And another difference, of course, is in Brazil, we expect if you come into hospital, there will be a different likelihood. You probably receive slightly different treatment to you would if you were in Peru compared to if you were in the UK. So that should be really taken into account. And a big issue, I mean, this isn't specific to Brazil in particular. This is specific to every single country, but case and death underreporting. So for sure, case underreporting is massive, but even death underreporting is quite substantial. I mean, if you look at the excess mortality statistics, so how many people are dying compared to on average, the numbers range from how many people are dying on average above what you would expect from COVID. The numbers range from a couple of percent to 100% more in different countries. So this death underreporting is a really substantial thing, because I mean, this is what all of our models are based on. They're based on the number of cases or the number of deaths. So it's absolutely critical to have good data for this. And there's a couple of other factors. For example, as Marcel said, Brazil is a huge country. It's more like a continent, so we can't really treat it as one entity. We really have to break things down at the state level. So that's what we're trying to do at the minute. And we're kind of still at a preliminary stage with Brazil, but I can present to you some results. For example, for Rio de Janeiro, and you can see here, this is the similar scenario to what we see in Sweden. So to my knowledge, there has not been a strict lockdown implemented in most states in Brazil. And what we're predicting is that the reproduction number is still above 1, which means we expect that the epidemic will, at least in the short term, continue to increase unless there are further measures taken to affect population behavior in terms of contact or in terms of mobility, or how people are behaving. So you can see that we're predicting very substantial numbers of infections, tens of thousands a day now in Rio, compared to the numbers that are being reported, which is, you can barely see on the scale. And this is estimated from the number of deaths. So if there's 0.5% of people who get the disease, who die, and there's 60 people dying, well then that's quite a big number of people getting the disease 3 weeks ago, and now it's an even larger number. So, I mean, there's a lot of people fitting different models, and there's a lot of predictions around on the internet. So something I would really like to do is just to emphasize the limitations of all of these models, but certainly our model has a lot of limitations. Just some of the limitations are the collinearity of the different covariates. So I said we account for things like whether or not the government has said you should close schools, or whether or not people should stop going to the shops. For a lot of these effects, they're extremely collinear and they happen at the same time. So, I mean, that's something of an issue. And another difficulty is, I mentioned as well, is taking into account the difference in contact patterns between different countries and different states. So in general, these contact pattern numbers between different age groups simply aren't available, apart from for a few countries, and the contact information is needed in order to calculate accurate infection fatality ratios, which is an essential part of our model. There's also other uncertainty. For example, in terms of the different distributions that we assume that link, for example, deaths to cases and cases to cases in the past. Now, as more data becomes available, to an extent, we can fit to these, and we've become less reliant on our initial priors. But I mean, all of this really comes back to a massive dependency on the data. And I mean, that's, if I emphasize one thing, it's that it's critical to have accurate daily death data and infection numbers that are presented every day. And yeah, that's the main thing. So in conclusion, lockdown is effective. It is identifiable. It's the one thing, unfortunately, that does seem to bring the reproduction number below 1 in most countries. In Brazil, I mean, the results I've shown you are extremely preliminary. We haven't published this yet, but it does seem like, for example, in Rio de Janeiro, that the reproduction number is above 1, and so in the short term, at least, the case death numbers are going to continue to go up. And just to emphasize it one last time, we really need accurate death and case numbers, so that's important. Thanks very much.
Thank you, Thomas. I think were brilliant presentations. While people raise their hands to make questions, I have my own list here, which is probably too long, but anyway, let me start with 2 questions for each one. Marcelo, I have two points here. One is how to handle the difference in policy responses when you try to translate the dynamics from one country to the other. And the second question for you is, you focus pretty much on the absolute number of cases, right? While the number of cases in a region that is larger or smaller than the others might make a difference, right? So why don't you use percentage of the population that is infected or something like that as a way of finding the time of the process itself? And for Thomas, I have 2 questions here. One is more technical one, is to what extent do you think that the distribution of gamma related to the Gs should somehow be associated with the trajectories of the Rs, or to what extent they are connected, right? Because the evolution of the successful case might be affected by the reproduction number itself. And the second question for you, which is a more general one, is how your approach compared to the traditional SIR methods, and what you think are the pros and cons here. And I think I have another question from Eduardo. Eduardo, let me, your mic is open. You can ask your question. Eduardo.
Sorry, can you hear me now?
Yep.
Okay, it's a question for Marcelo and Thomas. So it seems that the number of cases is critical, but there is an issue of missing detection in asymptomatic cases. In Brazil, and I believe other places, you detect cases that have any symptom. So there's also a selection bias on cases you actually detect. How does it affect? Can it affect the model and the conclusions?
Shall I start?
Thank you.
Yeah. Marcelo first, and then Thomas. Yeah.
And I'm going to ask the ones who are writing on the Q&A to raise their hands so they can make their questions, live. And please go ahead, you two, and then while people get organized.
Okay, so concerning looking at the percentage, I fully agree. We can do that. Thank you very much for the suggestion. That's kind of something that's easy to be implemented and to test and see how it will perform. Concerning the different policies, that's kind of an issue because there's different levels, for instance, of lockdown, as Thomas showed in one of his plots, and to mapping this for all countries, it's kind of a little bit tricky. What we tried, and we tried to use this mobility data from Apple as a proxy for the degree of lockdown, okay? And we included in the model, but we have a procedure that's kind of automatic to select variables. And for our surprise, this Apple data about mobility was not selected. So in this baseline model, so we removed, but we are kind of, this is something that's bugging us a lot, how to incorporate like different, not only different policies, but the way that people may change their behavior and impact of news or what someone says in the news, and how this affect the whole like degree of lockdown of a country. So the way we did it was like with Apple Mobility, and it didn't show up any predictive power. Okay, so that's the answer I have to you at this moment. Concerning Eduardo's question, of course this is an issue. What we are modeling, bear in mind, we have a reduced form, and what we are modeling is what we see and what's like pressing, putting pressure on the health system. So the cases that in the end of people that get tested, so these people that are kind of going to the hospitals, maybe people that need to stay in the hospital, some of them will need intensive care. So this is the variable that we are looking at. Of course, we cannot say anything about when the pandemic will end, okay? Or if we relax lockdown now, what's going to happen? Because we don't have a measure of these structural parameters of the system. So what we can do is what we do. It's like this short-term forecast for, let's say, the serious cases, the cases of people that really need some hospital care, and also the number of deaths. Okay?
Thanks, Marcelo. Thomas?
Yeah, I mean, I think Marcelo makes a really good point. We're coming at it from slightly different perspectives. I mean, he's predicting the important cases that are being recorded and affecting hospitals, whereas in our approach, we're trying to predict the total number of cases, if possible, and to see how far the epidemic has progressed. So it's a slightly different way of looking at things. On the question of does the number of cases reported affect our model? The answer is no, because we don't fit to cases, we fit to deaths. But underreporting of deaths is still an issue for us. Yeah.
All right. Thank you. Marcelo, I think your mic is open. Marcelo Fernandes.
Thank you. I have a question for Thomas. It's obviously very important to keep track of the population that can still be infected, keep track of us. However, I don't know, obviously I'm not a MD, but it looks to me that it depends a lot on individual immunity. And I'm not sure we already have hard evidence about immunity and whether it varies with how severe symptoms are. So it seems like logical to me that if you are symptomatic and you didn't show up any symptoms, perhaps you don't create anticorps. I have no evidence about that. I haven't read anything about that. Mm-hmm. But if you can comment a little bit on that, I would appreciate. Thank you.
Yeah. Right. Let me just take another one here. Eduardo?
Yeah. So it's a question for Thomas. Does the model have any way of accounting for levels of obedience for the public? Such as like if the government recommends social distancing, that you have any way of accounting for how much obedience how much people are following this protocol?
Okay, I mean, I can try to answer the obedience one, first of all.
Yep.
So we have different interventions and different intervention covariates, and these have different effect sizes. That's determined by the death data. I mean, so it's in the data, I suppose.
The other question? There's the other question probably.
And so the other question was about immunity. I mean, I'm not a medical doctor, so I don't specifically know about the process by which immunity might be acquired and how that differs for different age levels. I know that's being hotly debated at the minute, and to the extent to which immunity will last. I know the World Health Organization has recently said that don't assume just because you've had the virus that you will be immune. And that's an excellent point with regard to our model. So our model is the best that we can do at the minute, and it assumes that once you've had coronavirus, you're taken out of the reservoir of individuals that are susceptible to getting the disease. So at the start of an epidemic, this is probably a pretty good approximation. But as to how to include immunity effects, whether or not, the length to which immunity lasts, that's something that we can only include in the model whenever we get more hard epidemiological medical data on how long immunity lasts. But it's something we're thinking about, and it's a really good question.
Thomas, I got a question from Rafael, who has no mic there, and he's asking if the code for implementing the models is publicly available.
The code is publicly available, so you can download the code from GitHub and you can run it yourself to make these predictions. And you're free to adapt it and to do with whatever you want and try and make your own model. Yeah.
Right. And another question that I have in mind related to your presentation is you show that the lockdowns are the more effective ways of reducing the R, right? In the sense that, closing schools and other measures, they don't have such an impact on reducing the R. I wonder if the opposite is true, right? Given that we are in this situation now, if you open up schools, do you have any guess to what extent, the R will go up? And how do you think, it's the asymmetric situation between, dropping R and raising R? That's something that came to my mind. Not sure.
Is this for Marcel or for myself?
No, it's for the question, the results that you show in which you show that the lockdowns were more effective, right? The other measures they were not that effective reducing R. I wonder if the same would be true if we were talking to the opposite direction, right?
Yeah, I mean, if we assume that reopening schools has exactly the same effect as closing them, which isn't exactly obvious, but if we assume that, then it will bring R up a little bit. And for example, in the case of the United Kingdom, the R number at the minute is just below 1. And I think it would be pretty close to pushing it above 1, which would mean the epidemic really starting to rise again. And the problem is, if you push R above 1, and you're not just starting from 1 seed infection or 10 seed infections, but you've still got a population with 10,000 people infected, you
trigger different processes.
Yeah, it starts extremely fast. Yeah, it goes up extremely fast. So the second wave could be much bigger.
And the other question that I had here is to what extent your approach compares to the traditional SIR, simple deterministic models. What are the pros and cons with the kinds of results that you have?
Well, I mean, the thing is with SIR, there's SIR and then there's SIR. So there's like a whole range of SIR models. From the most complicated models with lots of different terms, which account for many things and are probably more sophisticated in what we're doing in a way. So we wanted to stay away from having 20 different differential equations and just try to keep things as simple as we can while still describing things. But in terms of the basic SIR, I mean, what we're doing here is actually equivalent in a way because we're including a population of susceptible individuals. We're letting them recover and we're accounting for infected. So it is actually in some sense equivalent to SIR, although some differences with SIR are that, we can easily include the effect of different intervention covariants and perhaps mobility and things like that, which I think might be a little bit more difficult. And I mean, it's different from SIR. I mean, it depends by what you mean, but everything we do is done in terms of Markov chain Monte Carlo. So we're not just fitting 3 parameters in an SIR model, although you could have those 3 parameters in the SIR model having some dependence, and you could make your SIR model stochastic as well. So in some sense it's equivalent, but in another sense it really depends.
Okay. Marcelo and Eduardo, you guys are with the hands raised. Have other questions? Yeah.
So let me do a follow-up question about SIR models. In a typical SIRD model, you have the beta parameter, which gives you the transmission rate in some sense, and then you have like the rate at which people recover themselves, which is normally gamma, I guess. And the RT would give you, I think, something like beta divided by gamma. So in your model, you just essentially model straight away R, right, directly. So there is no recovery rate or something like that. Am I getting it right?
Sorry, could you repeat the last bit there? So
in the SRD model, in the SRID, you have the recovery rate as well, right? And once you compute the RT, now they are not obviously the RT, you have to take the transmission rate, the infection rate, and divide that by the recovery rate, right? Do you get a similar relationship in your model, or apparently in the slides it seemed to me that you model straight away directly the RT in your model. I just want to confirm that. And I have a second question for Marcelo, because we have to make him work a little bit.
Yeah.
And it's a more of a technical question. So you have like obviously very little data. You're essentially doing a synthetic control using I1 variables, and for that you're using the error correction model. But I was thinking also about breaks. That would help you to increase the number of observations if you would have allow for common breaks and things like that. It's kind of a stupid technical question, but perhaps you have some ideas, or you have thought a little bit about that.
You mean structural breaks in the process?
Yeah, as the lockdown would be a break, right? If 2 cities at the same time are doing the lockdown, this could be reflected in the data.
Yeah.
As I'm just aware of the time, let's keep it short.
Yeah.
Sorry.
We will try. We
have 1 minute or so.
We tried with the mobility, like to mimic that. It didn't work, but we are going to try with it. Now that we have more data, like to have a structural break model.
Thanks.
So I mean, just to say that the renewal equation approach that we use is really simple, and it's basically equivalent to the normal SIR in so much as it has a term for the number of infected, the number of susceptible, and it has the reproduction number, and that's
Thanks.
Thanks.
All right. Thank you, everyone. I think it was a very insightful, and to me at least it was. I learned quite a bit. Next week we're going to have, as I said, Felipe Campante and Claudio Ferraz talking about the political economy of the COVID-19. So see you next week. Thank you so much for joining, and take care. Bye-bye.